So vector diagrams. In my last video I started sort of a small view. Okay, if you have a person standing here, say okay, and if you have a normal so that's a normal, that's gravity. You might have so the wind creates a force that way. So what I was trying to explain was if a person is standing in the ground, if the gravity is strong enough, normally when you're in the ground, the gravity pulls you down and the ground pushes back up. So you feel a bit of pull down, you have weight because the gravity is pulling down and normal is pushing up. If the gravity is strong enough, you'll actually be pulled into the ground. Whereas if you're standing, say, in a swamp or in quicksand, or you step into the water, if you step into the sea, you fall in because the density of the ground underneath you, the liquid is lower, is too low, and so the gravity can actually pull you down. Whereas if for some reason if you're getting, say, a space rocket, the force pushing you up is big enough, it overcomes gravity, so you get pushed upwards, okay? And you can have a force that way. So this is a basic vector diagram. So speed equals the scalar value, which is meters per second. So scalar is just basically a quantity, a size with no direction. Velocity, that is a vector, has direction, which is basically then you get the average velocity, which is the average speed in a particular direction. So it's the average in a direction. Okay, then you get the average speed, which is how much traveled. So distance equals speed times time. So speed equals d divided by time, okay? So how far you travel divided by the time taken. There's a lot of equations. These will seem easier once you actually start doing problems. These equations always, when you get lists of equations, they always seem intimidating, but when you start actually doing problems, it becomes easier because you start to understand it. It's always best to just do practice problems when you got lots of equations. It teaches you how to use the equations, it teaches you to understand the equations, and it teaches you how to understand problems, and it basically just helps. Average velocity equals the distance traveled in a particular direction divided by the time taken. Okay, so right, an example of all this stuff. Okay, so if a cyclist is cycling, goes 700 meters north and then turns and cycles 1,000 meters east and takes 400 seconds to do this, then calculate the distance travelled to the average speed, 3 the resultant displacement, and 4 the average velocity. There's a lot of calculation. So distance travelled, so this is all pretty easy. 1, so distance travelled equals the 700 meters plus 1,000 meters. Which equals, incredibly, 1,700 meters. Okay? Wasn't that easy? Just add up the two distances, the 700 and 1,000 meters. 2, so that's done. Okay? The average speed equals the distance travelled divided by the time taken, okay? Distance travelled divided by time. So it equals 1,700 meters divided by 400 seconds, which comes out at, if you use a calculator, 4.25 meters per second. Okay? So meters there, second below, seconds come up on top and you get meters per second. So the average speed is 4.25, 4¼ meters per second, okay? So that's the second one done. Okay? Does that make sense? So to get distance travelled, you just add up the distances. And you get the total distance. The average speed is the total distance divided by the time taken, 400 seconds, gives you 4.25 meters per second. And then the calculator, it would just do that divided by that, it comes out 4.25. Right, resultant displacement next. So we have to use a vector diagram for this. So we have okay, that's, and then okay, and then you have our, so 700 meters up, 1,000 meters long, X, okay, that's north, south, east, west, okay. So we're using a scale vector diagram. Actually, I was meant to use a scale vector diagram on this to use a protractor, but I don't have a protractor. I'm going to do it in another video, so I'm using Pythagoras instead. So to work out ABC, okay, I want to work out AC, the distance A to C, okay, you call that like that. So AC squared equals AB squared plus BC squared, which equals 700 squared plus 1000 squared, which equals 49,000 plus a million, okay, which equals 1,490,000, okay. So AC equals the square root of 1,490,000, which equals 1220.7 meters, okay? So this is using Pythagoras. Okay? It gives you that distance being 1220.7 meters, okay? And then to work out the angle, because we want to get the resultant displacement, we got the opposite and adjacent sides of the triangle, that's being the right angle. That's adjacent to the angle, that's opposite to the angle, okay? So Pythagoras applies to right angled triangles. So you got opposite adjacent, the square of this side plus the square of that side equals the square of the hypotenuse. That's why I done AC squared equals 700 squared plus 1000 meters squared, which gives you AC at 1220.7. And then to get x, we go tan x equals opposite over 700. So x equals tan minus 1 of 1000 divided by 700. Which equals tan of 1.429, so x equals 55.0 degrees, okay? So using tan, which is opposite over adjacent, you get x value of 55.0 degrees, okay? So that's the resultant displacement. So the resultant from A to C is 1220.7 meters, which is that's east of north, okay? So it's going north and then east, so it's east and north. So that's the resultant displacement. So you're going, that's northward, but you're also going east, so it's 1220.7 meters eastward of north, okay? So that's resultant displacement done, okay? And now the average velocity you've got to work out. So that's time, distance travelled divided by time taken. So okay, so we got so the displacement is 1220.7 meters divided by 400 seconds, which comes out at that's actually at 55 degrees east of north, okay? So that comes out at 3.1 meters per second at 55 degrees east of north. Okay? When you put these through the calculator, you get 3.1. 3 times 4 is 12, so this is 3 times and a little bit more, so 3.1 meters per second at 55 degrees east and north. Okay, so that's the average velocity, okay? That's why I've done distance covered with displacement divided by time taken. Does that make sense? This is the average velocity, which is distance divided by time. That distance moved up divided by the 400 seconds gives you this, moving 3.1 meters per second at 55 degrees east to north. Okay? Right. So, example 2. So a yacht, a sailing boat, a yacht, travels north at 2 meters per second, okay? The tide is west to east at 1 meter per second. Okay, so what is the resultant? Resultant vector of yacht. Okay, so if you're in a sailing boat, it's travelling 2 meters per second north. Tide is moving west to east 1 meters per second. So what's the resultant? So you maybe do it. So you have to draw a vector diagram again. So you have north, south, east, west. Okay. So you have that's north is 2 meters per second, and that's 1 meter per second west to east. Okay. So you have, so basically it's going that way times that way. So the resultant is this, okay? So, and there's an angle x involved up from the east, the x-axis. So the yacht is basically pushed, although it's going north, although the yacht's moving northwards, it's being pushed east, okay? As it sails north, okay? So what you say is that you have, so that's A there, B, and that's D, okay? So you have, maybe I should put these in red, it's a bit clearer. So you have, so that length, that's 1 meter per second, and this is 2 meters per second, okay? So so you got B, that's D, so B, that length, is parallel to AC, okay? That length, and AB, that height, that length north, is parallel to DC. CD, DC, doesn't matter, okay? So BC is parallel to AC, okay? And the size, the magnitude of BC, so BD equals BC equals AD, so BD equals AC, which equals 1 meter per second, And the magnitude of AB, you write magnitude as these two bars either side, equals magnitude of CD, which equals 2 meters per second. Okay? So that's equal, those lengths are parallel, these lengths are parallel, length of that equals length of that side equals length of that side, okay? So, so we know that AC, so AD squared by Pythagoras, this length is equal to AC squared plus CD squared, okay? So that length is equal to the square of that plus the square of that, which equals 1 squared plus 2 squared, which equals 5, okay? So AD equals the square root of 5, which equals 2.2 meters per second. Okay? So this length is equal, this is by Pythagoras. So that length, square of that plus the square of that equals the square of that. The square root of AD is 2.2 meters per second. Now we've got to work out the angle here to get the actual displacement, okay? So we know that length of that, we know length of this, so we can use tan. We could use sine and cos, but we'll use tan because we know these lengths. So tan x equals opposite over adjacent, which equals CD over AC, which equals 2 over 1, which equals 2, okay? So x equals tan minus 1, 2, which equals 63 degrees. If you put that through the calculator, the inverse tan, you probably have to press shift. So if you press the shift button, shift tan gives you the inverse function. Shift tan gives you the inverse function, and then press 2, you get a value of, can you see that? 63.4 degrees. Okay, I'll leave it at 63. Therefore, the resultant this is velocity is equal to 2.2 meters per second at 63 degrees. So it's 2.2 meters per second at 63 degrees. That's north of east, okay? North of east direction. Okay? Because we're travelling north and we're being pushed east, so it's north of east. East that way, so the north of east direction. Okay, so that's another example out of the way. And one more example, a lot of examples. So another example. So a car travels so I'll try to make this one quicker. Car travels 20 meters per second east, okay? Raindrops are blown across the windscreen at 0.1 meter per second, okay? Which equals 10 centimeters per second. They go due south, okay? So calculate what's the resultant. Calculate resultant velocity of drops, okay? So the solution is so you have So you have this is 20 meters per second east, okay, and raindrops are going due south 0.1 meters per second, okay. So you got, so this is a vector diagram. So to work out A, B, C, D, so the length of AD squared equals A B squared plus BD squared, because that's parallel to that, that's parallel to that. The lengths of these are the same, and the lengths of those are the same, okay? So AB squared is 20 squared plus 0.1 squared, which equals 400 plus 0.01, which equals 400.01. So AD equals the square root of 400.01, which equals 20.00025 meters per second. Okay? So I know it seems a very small amount, but and then if you've got x there, okay, the angle, so you got tan x equals adjacent, which is slightly wrong. Adjacent is actually 0.1 meters per second over 20. So what's tan 0.1 divided by 20 equals 0.005. Okay, so inverse tan 0.005 adjacent. Oh, right, okay, so it's the so we're heading car 20 miles east, that's going south, so it's actually this angle you want, that angle, so it's adjacent 20 divided by 0.1, which equals 200, so x equals tan minus 1 200 equals 89.7 degrees. So yeah, so it's adjacent, which is this, over the opposite, which is 0.1, gives you 89.7 degrees, the angle, so that's 89, so it's it's actually almost the raindrops, although you're driving east, the raindrops are being moved due south. So it's actually, this is wrong, that is actually, this resultant should actually be virtually going down the y-axis. So although you're driving east, the raindrops are actually being blown this way, so it's kind of a bit, it's only diagrammatic, but I should have really drawn the resultant more like that, okay? Not like that, but it doesn't really matter. So it's 89, okay, so it's almost right angles to the direction of travel. The raindrops being blown at almost right angles to direction of travel. So yeah, so the resultant vector, the resultant velocity equals 20.0005, sorry, 20.005 20.0